I teach a college course on quantum computing at Carnegie Mellon University. It's the first week of the semester. And the first time people learn about quantum computing, they're often taught it using linear algebra and vectors and unitaries and tensors, and it's like a little bit of complicated math. But I figured there's a really easy way to explain it, where it's nothing more than regular old computing plus one extra instruction, one extra bit of code that lets you do quantum things. And it's simple enough that I was able to make a quantum computing simulator here in my favorite programming language, which is Scratch. And in fact, this is the one extra instruction, H.A.T, that makes it quantum. That's not its real name, but we're going to call it H.A.T for this demo. So let me show you a bit about how it works, and we'll explore. And I put a link to the Scratch program in the description, so you can also go and check it out. Don't try to hit green flag to run it. You have to actually go into the editor, like I'm doing here, and you can mess around with the code. So this is a little instruction for you. Let me get rid of it. And actually, let me delete most of the instructions. We'll bring them back, but we'll build up to it later. So just imagine there's a bunch of new blocks you get, or a new programming language, and you're trying to figure out what it does. So I'm going to delete everything here, well, except for the first two instructions. Okay, so the first one is restart. I'm not going to lie to you, that just restarts things. So if I click on that, everything's restarted. Now, the first main instruction you need is this thing called make a thing named my thing. And I've called these things in this demo. You can think of them as variables and codes, or wires if you're more used to building circuits and things. And really, it's standing for a qubit. But in real life, a qubit in a quantum computer might be represented by a photon, or by an ion trap, or a superconducting whatnot. So there's many different ways of trying to implement it physically. But just for the purpose of coding, I'm going to call it a thing. So if I click on this instruction, I can make a thing called my thing. Or I can make another thing called, I guess, I don't know, X is a more normal variable name in programming, so I can make a thing called X. Actually, I was demoing this in my class, and I said, before we go on to learn about the next instruction, if you were a software engineer in test and trying to figure out, does this work properly, or what do these things do, what would you try before going on? And to my great happiness, one person suggested the exact thing that I hoped you would try, which is to try to make two copies of the same thing. So let's try that. I'll click on this again. Oh, and you see it says you can't do that. There's already a thing named my thing. Well, that's not too sad. Maybe it's to be expected that you can't have two variables with the same name, but you can have a bunch of different variables if you want, but not two copies. Okay, that's great. Nothing too special. So let me introduce you to some new instructions. Let's get out this one. Print all the things. And actually, there's one variable I'd like to bring out too, which is this one, output. Okay, let me go back to the blocks. Okay, so we've got a bunch of things or variables, and okay, well, now that we have this new block, print, let's do it. So let's print all the things. Okay, besides making a sound effect, we see that our things, my thing, X, and Apple have the values 0, 0, 0. Okay, so I guess, variables are initialized to 0. Also, if you click this output, that's a variable, you see it, we got these values 0, 0, 0. Okay, I also asked the class, okay, what should I do now? And one person said, oh, print them again. So let's print them again. Oh, nothing happened. Is that a bug or what? Not sure. Well, let's repeat it. So let's make a thing called my thing and X, and let's print now. Okay, my thing and X are both 0, 0. Yeah, that's the output of 0, 0. And actually, oh, you see there I clicked on make a thing named X, and we saw before that you cannot make two things with the same name, but it let us make this variable called X. So let's print. You actually kind of see that after you print things out, they sort of no longer exist. So kind of printing a variable sort of also deletes it, seemingly. Okay, well, that's fine. Anyway, we're not really doing any computing yet. We're just bringing in some variables, and they seem to have value 0. That's not interesting. So let me get two more instructions out. We have add 0 to thing and add 1 to thing. So let's restart here. I'll make a thing called X and add 0 to X. Well, you're not going to be surprised to learn that adding 0 to X doesn't actually do anything. This is actually a useless instruction, but there's a reason I have it in there. Let's restart just to be sure. Now, when I asked my class to play around with this, the first thing the student did was they added 1 to X 3 times. So let's do that. 1, 2, 3. And now let's print it and see 3. Oh, not 3. It output 1. That's a little funny. You might think about why that's the case. Well, let's do some more proper testing here. Let's make a thing called x, and let's double check. Okay, it's 0. Let's make a thing called x, add 1. Now it's 1. That seems normal. Make a thing called x. Let's add 1 twice. 1, 2, 0. Okay. We saw 3. It turned it to 1. Let's do 1, 2, 3, 4, 0. 1, 2, 3, 4, 5, 1. You probably got the gist of it. It's like a toggle, actually, this add 1 to thing. Really, it adds 1 to the number x, but, you know, mod 2, just like this classic Scratch block. Oh, yeah, mod 2. Or if you'd like to think in terms of Boolean logic, honestly, these, you know, things are storing bits, 0 or 1, or you can think of it as like true and false. And adding 1 to the thing x is really like replacing it with its not, its negation. But I like to actually think of it as like adding 1 to the number x, but then we take the remainder upon division by 2, or we take dividing by 2. So this is something. We're still not really doing computing. I mean, we can set variables to our favorite Boolean bit values. Like if I make x and my thing and apple, and I want to set them all to 1, I can do add 1 to thing x, and add 1 to my thing. And I can do add 1 to apple. Well, let me just not do that. But if I print all the things, you see x and my thing are both 1, and apple is 0. Okay, well, we got the gist of this too, so let's move on and learn some more things. Now, here are where the instructions where we really get computing. Let me just free up some space here. With these 3 instructions, and let's take a look at them. Add blank and blank to thing, add blank or blank to thing, and add not of blank to thing. And if you've done a little bit of computing, you know, your spider sense should be tingling. We've got like an and an or and a not. And like these are basically the logic gates that we always use when building logical circuits. And you might know that, you know, as long as you have and, or, and not gates, you can kind of compute anything. And, you know, normally you would expect this instruction to say something like set thing x to the and of 2 other things. And instead it does this slightly funny add the and of 2 things to x, or at least seemingly it does. We'll test it. But that's not such a big deal because, you know, let's say we want to, I don't know, set x and y to both 1 and then compute their and. So let's make a thing called answer, maybe, for the answer. And we'll make a thing called x and a thing called y. And, okay, so let's add, not add 0, let's add 1 to x. Right? And add 1 to y. We can like stack all these like, you know, whoa, like with standard Scratch style. So let's do that. We'll add 1 to thing x. We'll add 1 here. Let's make our answer. Okay, so we did all that. And you see if we print all the things now, yeah, 1, 1, and 0, just as intended. So now we'll like add the and of x and y to thing answer. Okay, and maybe we'll print all the things. Yeah, 1, 1, and 1, maybe as expected. And actually, let's not make 1 y equal to 1. So if we printed all the things now, okay, x and y are 1 and 0. And if we like ANDed them together, you know, by the rules of logic, we should get 1, 0, 0 again. But if we made this or, let's do that, x and y to thing answer, and we print this. Okay, 1, 0, 1. So it works as expected. I won't test the NOT gate, but you can take my word for it that it works just as expected. So actually, as you may know, or as I mentioned, you know, once you have the ability to do AND gates, and OR gates, and NOT gates, you can compute any kind of Boolean function you want. And in fact, whenever you code in, like, I don't know, Python or whatever, it gets transpiled into C, and that gets compiled into assembly language, and you can convert assembly language into Boolean circuits. And so really all of regular old, you know, programming, all of regular old computing can be done with AND, OR, and NOT gates. And therefore, you could say that, like, at this point, we have a complete regular computer simulator with all these gates together, we can do all the, the coding we ever want to do. Okay, well, this is about quantum, so now it's time for the last instruction, and this last instruction is called H.A.T. And with this instruction on the board, we now have a fully complete quantum computer. Using only these blocks, you could do anything a quantum computer could do. You could do Shor's factoring algorithm, Grover's algorithm, the whole works. So, yeah, what is this H.A.T? I guess let's try to click it. Whoa, so exciting. Now Cosmic the Cat is wearing a hat and the background is blue. We're in the minus world, maybe. I'll let you figure out why it's called the minus world. That's a little joke. So what should we do? So I asked, the students, what should we do? And they're like, oh, do H.A.T again. And, oh, is it back to normal? Who can say? Okay, well, let's try to mix this together with programming. So maybe the first thing to try is, okay, we'll make a thing called X and print it. Let's just make sure nothing crazy has happened. Okay, X is 0, good. So, the students suggested now let's make a thing called X and H.A.T. And let's do it in steps just so it doesn't run all at once. So we're going to restart, make a thing called X, H.A.T. Ooh. And now let's try print all the things. 0. Okay, so maybe H.A.T does nothing. Now actually a student in this class suggested a very good idea, which I liked, which was restart, make a thing called X, H.A.T, now make a new thing called Y. Interesting move. Let's do that. Well, let's just click it. And now print all the things. Oh, did I maybe not click X? Let's try this again. Restart, make a thing called X, H.A.T, make a thing called Y, and print all the things. Okay, yeah. Okay, so X is 0, Y is 0. So yeah, maybe you at this point think X does nothing, right? So let's just check this, make a thing called X, H.A.T, and print all the things. Okay, cool. I was hoping it would actually act differently. Aha! What just happened? I did the same thing I was always doing, and now suddenly X is 1. Let me try that again. 1. Okay, let's make some code out of this. Restart, make a thing called X, H.A.T, print all the things. I mean, if H.A.T does nothing, then we should just get 0, but okay, we got 1. Now we got 0. Aha, you might be saying, oh, I heard about this quantum randomness. It seems that after we do this, we get a random value for X. That's interesting. So maybe if you do H.A.T, it makes the variables random. Well, this is for you to play around with and think about. Let's just try a little bit more things. Maybe we'll turn X to 1 and then do the H.A.T. In fact, you might get, wondering if this really is random or what, and I actually have some code to help check that out. It's down here. Okay, let's restart just to make everything clear here. Now, what does this code do? It basically does that little program. You can see it here in red. It restarts, it makes X, it does H.A.T, it prints, and then it just keeps track of how many times it saw 1. So it changes this variable total by output, which is either 0 or 1. And we're going to let's do 100 trials just to warm up. And if you were to, and at the end, it computes the fraction of trials where the outputs were 1. Now, don't click go now because it'll, do the crazy H.A.T sound effects 100 times. So I have a way around that. There's actually toggles for the sounds and the talking and the visuals. So if you hit S, I thought if you hit S, yeah, S, T, and V. Let's turn everything, all the wackiness off. So it'll just silently run the code. And let's do it. Let's try that code 100 times. Oh, okay, 61% of the time we got a 1. Let's do it again. 43% this time. 58% this time. Let's do it 10,000 times. Waiting, waiting, waiting. Okay, so just over 50% of the time it was 1. So it would seem that if you make a thing called X and then you H.A.T, then that randomizes 50-50 X's value to 0 or 1. So far, that's not very special. I mean, we have random number generators on our regular old computers, so this does not seem like a very interesting situation. Let me restart here. But let's just do some, other little experiment to make things interesting. Let's make a new thing called, some little thing. Okay. Oh, I guess I told it to not have really long names. Okay, we'll abbreviate that to some little thing. Okay, so let's make this some little thing. And we'll do the hat. And now we kind of know this should be like 50-50 random. I mean, that's what it seems to do. Now let's actually double this. Let's get a double into the situation. Let's do hat 2 times in a row. Well, let's do it one step at a time. So we'll restart. We'll make this thing hat again. Is it like extra random now? Is it randomized and then randomized again, so it's kind of the same? Let's find out. We'll print all the things. Okay, this some little thing is 0. Let's try that again. Make the thing, hat again, 0. Make the thing, hat again, 0. Kind of funny, right? We know that like after you just had it one time, you get a random value. There's 1, 1, 1, 1, not too random. 0. Okay, well, sometimes that happens. Getting a lot of 0s and 1s. Okay, but if you do it twice, watch what happens. 0, 0, 0, 0, 0. Seems to always be 0. Actually, I didn't try this, but let's go back down here. Let's turn off all the sound effects and everything. And we'll just call it X, as we always do, but let's hat twice and see what happens here. If I run it, let's do 1,000 times. Let's not make ourselves wait too long. And let's try it. It's thinking 0 of the outputs were 1. But isn't that crazy? Like, if the hat randomizes the value of the thing X, and then you randomize it again, how does it always 0? Does it, like, remember what it was? In fact, we can try a slightly different experiment. Let's make this a thing, and then we'll add 1 to it. Okay, so we'll randomize it twice, starting from the value of 1. And it was 1. 1 again. So it seems like it somehow remembers that it came in at value 1. Whereas if you just had it once, well, it seems like it's random. So actually, this is a good time for you to like go into this, Scratch program and mess around and, try to figure out what hat does. Try some more complicated experiments than this. As I mentioned, it does, something that actually corresponds to a real-world operation you can do on your photons or your electrons or your ion traps. And it changes their behavior in a certain way. And you can really make physical experiments that correspond to any code that you make here with Scratch blocks. And you can literally, see what happens in the real world. And, the Scratch version is just a fast way to do that and try to learn about what this hat does. So as I mentioned, this gives you the full power of a quantum computer, and you might be, thinking, all right, so quantum computers are supposed to do like amazing things or be able to solve problems really fast. How does that work? And well, you'll have to play around with it and find out. But I do want to show you one kind of demo to intrigue you. So to maybe illustrate the power of having this quantum instruction called HAT. So I'll have some more code over here that should help. Let's go or scroll over. Okay, so here's the situation. I'm going to make 6 variables, 6 things called x1 through x6, as well as another variable called answer. And I've got like a mystery block that I've defined here. So this is like a make your own block in Scratch or like a function in a regular programming language. And I have 6 instructions here, which are all the form add thing x1 to ants, add thing x2 to ants, add x3 to ants. Oh, I forgot. Maybe I didn't intro this instruction, but there is an instruction called add thing x to thing y, and it does what you expect. Okay, and all the way through add thing x6 to ants. And here's a game I want to play. I'm going to define mystery block to be some combination of these things. So I'm going to choose a subset of the 6 possibilities. So here I've got x1 and x3. So now if I do this mystery block, let me just bring in, let's say, a restart. Whoops. And I'll make all these variables. And now if I click mystery block, it'll add x1 to ants and it'll add x3 to ants. But x1 and x3 are already 0, so I don't know. Let's set them up so like I'm going to add 1 to x3. Now let's add it to x1. Okay, so if I do this, x1 will be 1. Then if I do mystery block, it'll add 1 to ants and it'll add x3, which is 0 to ants. And then let's print all the things. So let's do that. I'll do this restart. And let's do the mystery block. Ta-da. And now let's print all the things. And let's see. Yeah, so let's see. You can see x1 was 1 and x3 was 0. All the other ones were 0. But we added x1 and x3 into ants, so it became 1. And so if we added maybe also, if we change this to add x3 in, let's rerun it. We'll do the mystery block. And we'll print all the things. Now you see x1 and x3 are both set to 1, but we added both of them into ants, so that toggled it twice, so ants ended up as 0. Okay, so far so good. Nothing too interesting going on. Now, as I said, I want you to imagine the situation where this block is a mystery. Somebody chose to put some, but not necessarily all of these commands into mystery block. So in fact, let's play a little game. Let's, if you're watching this video, close your eyes now, and I'm going to put some, but not all of these commands into the mystery block, and we'll see what happens. Okay, keep your eyes closed, keep your eyes closed. Okay, so you can open your eyes now. I've defined mystery block to have some subset of those things in there. And the goal now is, try to figure out which commands, which of x1 through x6, if any, I put into mystery block. And I guess there's 6 of them. So each one I could have chose to either put it into mystery block or not put it into mystery block. That's 2 possibilities. So there's 2 to the power of 6 different possibilities for what mystery block is doing. Well, it's actually doing one thing, but I could have chosen from one of 2 to the power of 6, which is 64 possibilities. So there's 64 different possible mystery blocks, and maybe your job as like a detective is to figure out which variables I'm adding into the answer thing in mystery block. And you should try to use mystery block as little as possible. It's kind of like a game of 20 questions. How many times do you have to call mystery block? And it would be very unlikely that you could do it just by using mystery block one time. For example, let's say we run this code. And now we'll do the mystery block. And actually, the only thing I've done here is add 1 to x1. So all of them are 0, except x1 is 1. Now I'm going to do the mystery block. Okay, we don't really know what happened. Now let's print all the things. Let's see. So x1 is 1, as expected. All x2 through x6 are 0, as expected. We didn't do anything there. And answer became 1. And what can we conclude from this? We can kind of conclude from this that whatever I put into mystery block, I must have used the instruction add x1 to ants. Because if I didn't use the instruction add x1 to ants, then how would ants get 1? Like all the other ones had value 0, so if they're in the mystery block or not, it doesn't really affect ants. Ants can only change if I have x1 in there. So basically, I've learned that, okay, mystery block does contain add x1 to ants. So I've actually cut down the possibilities from 64 to 32. Like I know x1 is in there, but I don't actually know anything more about x2, x3, x4, x5, and x6 because I set them here to 0. So, if they were in there or not, it doesn't really affect what happened to ants. Let's restart and let's try to prod the mystery block a little bit more. Actually, maybe I shouldn't have restarted, but anyway. Let's try to prod it a little bit more. In fact, let me set all the variables to 1 and then sort of test mystery block. Let's see, 1, 2, 3, 4, 5, 6. Yeah, I'll print all the things at the end. So let me just quickly type this, x3, x4, x5, x6. Actually, let me take this off. Okay, so here I'm going to set all the x's to 1. Okay, and now I'm going to do the mystery block, and I'll print all the things. And let's see, they were all set to 1 as expected, and answer ended up 0. So think about that. What does that mean if answer ended up 0? Well, whenever I did an add x something to answer in the mystery block, it sort of toggles answer, and it ended up at 0. So it means I must have put in an even number of instructions into mystery block. I must have did, add x something to answer an even number of times, because then every time that instruction executes, since the appropriate x had value 1, it toggles ants, and it got toggled an even number of times. And if you think about it, that's also like one bit of information. It also cut down the possibilities for mystery block from 64 to 32. And so, okay, we learned it's an even number of times. By doing this and trying mystery block, we learned that it includes x1, and that actually means it's down to 16 possibilities. But as I said, it's like a game of 20 questions, and you can kind of tell that every time you do mystery block, you know what the values of the x's were coming in. And so the only thing you don't really know is the value of ants, and so you learn that ants is either 0 or 1. And so you kind of get back like one bit of information, like one yes/no answer. And so to cut it down from 64 possibilities to one possibility and figure out what mystery block really is, you would have to ask like 6 questions, or you'd have to run this mystery code 6 times. Let's actually just remind ourselves what it was. Spoiler alert, if you really did close your eyes, I used x1, x3, x4, and x5. So indeed, x1 is in there, and there's an even number of instructions. Okay, so what's quantum? Well, you see, we haven't used any of our quantum instructions yet. And now I really want to show you like a party trick, like the power of quantum. So here's what I'm going to do. I'm actually going to only use the mystery block one time, and I'm going to figure out what the add instructions are. How am I going to do that? I'm going to add 1 to ants. Why I do that, maybe it's not so clear. But we're going to hat. Now we're going to mystery block. And now we're going to hat again. Let's just do it a little bit more slowly, actually. Okay, so let's reset. Here's what mystery block actually does. So we're going to hat. And we're going to do this mystery block one time. Hat again. And now let's print. Check this out. It's a little bit crazy, actually. Remember, we didn't change any of the x1s going in, so they were all zeros, but they came out with zeros and ones. Now, ants, we set it to be 1 here, and it came out 1, so that's not too unexpected. But look at the other x's. We have some 1s here. We have a 1 in the first position, the third position, the fourth position, and the fifth position, x1, x3, x4, x5. And wait a second, take a look at this mystery block. It added x1, x3, x4, and x5. So it would seem that just doing this, using mystery block only once, we figured out what was in the mystery block. Let's try this again just to make sure it wasn't a fluke. Let's change mystery block. I don't know, just delete this stuff. So that's, I don't know, x1 and x2. Okay. And let's run the code. So we set ants to 1, everything else is 0. We're going to hat. Do the mystery block one time, and then do the hat again. And now we'll print. And take a look. Okay, answer is still 1, but for the x's, we have 2 1s, x1 and x2. So in fact, just by adding like these 2 hat commands, these 2 hat blocks, we were able to completely figure out what's in this mystery block out of all the 64 possibilities by only running the code mystery block one time. And as I kind of described before, if you didn't use the quantum power, it'd be like a game of 20 questions, and you'd have to run mystery block 6 times. And now we kind of figured out what's in mystery block by only running it one time. So we kind of got like a 6 times speed up. And really, this is kind of the power of quantum computing, particularly if there were like 1,000 things rather than 6 things, we would have got like a 1,000-fold speed up. Now, this is a bizarre scenario, honestly. Like, I've got this mystery block and we're trying to figure out what's in it, but I hope it convinces you that there is some power to be gained, some real amazing computational power to be gained by using these quantum instructions. And exploiting this strange power is really what quantum computing and quantum programming is all about. So let me stop the demo here, and let me just suggest to you a fun thing that you can try is really, go to this Scratch quantum computer that there's a link for in the description, and just try to play around with the instructions and see if you can figure out what this hat instruction really does. Make a hypothesis, test your hypothesis, revise your hypothesis, and do some more experiments. And if you do this, it's really exactly like as if you were a quantum scientist, or I guess just a scientist in the 1920s, doing the first kinds of quantum mechanics experiments and trying to deduce the laws of quantum mechanics by physical experiments. That's exactly what's going on here when you're playing around with this quantum computing code and trying to deduce what this mysterious hat instruction does.